Okay, hey everybody, welcome. We're a couple minutes in, so we're going to be a little bit tight for time. Got a lot of content for you today, but thanks for making it, especially during lunch. So my name is David Burrell, and this is my colleague Neil Bedekar. We are both tech leads on the developer platform team at Meta for the Reality Labs division. So we both think a lot about performance analysis and optimization on Quest. We've both been here a long time. I've been here for, wow, 12 years now. Neil, what have you been, 8?
8.
Wow, okay. So yeah, we've seen a lot of you, and I see a lot of familiar faces here. You know, kind of get your sea legs in VR and ship a lot of amazing things. But if you're just getting started, we also have a lot to talk about. So today we'll be covering what you probably came for, which is maybe some best practices for how to maximize your frame rate, how to hit your performance targets more easily, also maybe some targets you should be shooting for in terms of CPU, GPU, memory utilization, and so on, and also some of the tools that are available. And we'll also talk a little bit about some of the things that Meta has been doing for you to accelerate all of that. So one of those is AI. If you were just here for that AI talk, you get a bit of an overview of what we have. We'll go into a little more detail on the performance aspect of that. And we'll also talk about Link and some of the other things you can do with our infrastructure-related tools to deal with performance once you ship. So let's get started. So right off the bat, you know, we should point out that VR is a very important consideration. Performance in VR is the difference between comfort and discomfort, and that can really hurt your user engagement if it's not there. On the other side, you know, a more performant, responsive experience can be more emotionally engaging and drive your user experience, user engagement up. So there are a couple of metrics to keep in mind. When we think about responsiveness, one of the main drivers of problems there is dropped frames. You have a limited amount of time every frame to render on the GPU and the CPU. Typically, game engines like Unity and Unreal are pipelining a series of operations for multiple frames that are in flight. And all of those pipe stages, you know, have to fit in 13.8 milliseconds, really, to hit the deadline. And then you look at system contention. If you're over like 70 or 80% of your GPU, of your CPU headroom, you're actually going to run into trouble anyway, just because there's jitter in the scheduling and things like that to worry about. So it's really easy to drop frames, and just a couple of dropped frames in a row will make your users so uncomfortable they may not want to continue using your app. So fortunately, you have a few levers here. You can render anywhere from 120 frames per second, which is extremely responsive and smooth, down to 72 frames per second, which is where a lot of people ship, frankly, because it's just easier to hit that frame rate. If you go below 72 frames per second, you start getting users complaining about flicker. The headset does do 60 frames per second, but with the exception of some media use cases, that's really not recommended for app submission. And once again, if you have like storms of dropped frames at any point, the user is going to start noticing as soon as there are 2 or 3 dropped frames. So it's really important to keep tabs on this. And it's often not sufficient to do it as an afterthought. You kind of have to watch the performance throughout development and have submission scripts that check if your brilliant tech artist got a little overambitious, tessellating a toroid or something. So to manage those frame times, we look a lot at things like how many pixels are you rendering, meaning what is your render scale. When you use OpenXR, or if you're using Unity or Unreal, we layer on top of this, you have a render target that every draw call is rendering pixels into. And draw calls are kind of the indivisible units of rendering that you fire off to the GPU. So you have these batches of polygons that have materials on them, and in Vulkan, that comes out as a draw call. So we look at how many draw calls you can issue per frame as one metric. Generally, the guidance is to stay under about 500, but that is not at all a hard and fast rule. You could go well above 1,000 and still make it work if you're really smart about cache locality and making sure that you're using the right shaders and the right access patterns and everything. But we have a nice write-up of that by Trevor Dash that goes into a little more detail on the trade-offs there. Anyway, quick rules, below 500 draw calls, trying to use below 85, above or equal to 85% render scale, meaning we have a dynamic render scaling system that can allow you to render at a baseline pixel density, which is like the recommended resolution for the screen. And then when there's extra headroom available, the performance can be scaled up to give the user extra sharpness without dropping frames. And then the system will intelligently like scale back the resolution to the foundation that you set. So we recommend about 85% as a target on that. And again, staying below 70% CPU, 80% GPU will keep you clear of sporadic contending tasks there. It's also important to note that although you have more than 5 gigabytes, I should be specific, available, it's better to stay below that because sometimes fragmentation or other sporadic allocations can compete with your app. So, okay, those are some of the things to keep in mind when you're trying to stay within your budget. But how do you do that? So here are some techniques that we often recommend. One way to save pixels that you're rendering is to render lower resolution in the edge of the screen. And a lot of other GDC and SIGGRAPH and so on talks have covered this in detail. The most popular method today is a method called fragment density map, which we've worked on with Qualcomm. And that kind of defines different regions of the screens that'll get different levels of decimation in terms of the pixel density. So generally in the center of the screen, that's where the user is the most sensitive. The user tends to be looking the most closely. And so we render that at approximately double the resolution of the outer portions of the screen. So definitely use fixed foveated rendering to save GPU. Application SpaceWarp, of which Neil was a major author, we have a technique that will look at frame-to-frame motion, which you actually provide us, but we've provided you with shaders and a bunch of rendering systems to compute that so you don't have to think about it. But basically, your app gives us motion vectors that we extrapolate to fill in every other frame. And that can literally save you up to 70% of your CPU and GPU if you use it. But you have to be mindful of it when you're writing your shaders and designing your game. We also have MetaQuest Super Resolution. So this is one of those upscaling algorithms that we do in the compositor. And in this case, we're using deep learning, and we have additional detail we can fill in in the compositor. If you're used to FXAA or SMAA, you'll be familiar with this type of approach. But if you're doing deferred rendering, actually I have a question. How many of you are using deferred rendering? Okay, very few. And that's probably expected because, really in VR we've been, and I think everyone has been kind of advocating forward rendering because of its simplicity and the limited resources and the tiled rendering constraints that we have typically on mobile VR. Well, more and more titles are starting to think about forward plus, post-processing, and deferred rendering, and in those cases, it may be more logical to use temporal anti-aliasing, which actually is a great way to do it on VR because it is statistically correct, unlike, for example, FXAA, which may cause binocular disparities by converging to different values for the different eyes. Anyway, temporal anti-aliasing is one way of getting sharpness without actually increasing your resolution. One thing to note is that in the past, on other Qualcomm GPUs that we've shipped with, 4x MSAA has been the guidance. And indeed, if you query recommended MSAA level from our API, it will tell you 4 because we didn't want to break anyone. But I recommend you use 2x MSAA now. And if you want additional sharpness, you can use techniques like temporal AA or super sampling to get that added sharpness, rather than cranking it up to 4 at this point on our XR2 Gen 2 hardware. Okay, so now we have Neil, who is a true GPU performance expert.
Thanks a lot, David. And what David really did the last few minutes was set the stage for why performance is pretty high stakes. It can't just be an afterthought. So a lot of you, either previously or especially now, you have a newfound interest in probably optimizing GPU performance. What's the very first thing some of you might turn to? Just shout out a couple answers. Turning on, right? Perfect. And how might you even find some of the areas that your app is losing performance today? So what we were looking for here is just use performance tools. What are some of your favorite performance tools that you use on Quest today? Okay, RenderDoc is great. Next 10 minutes are all about RenderDoc. So I hope a lot of you might find something new, but specifically everyone else in the audience, who isn't using it might learn a couple tricks in the workflow. What else do you use right now? What? What was that? Oh, okay, from within Unity, engines like Unity? Perfect. So these in-engine profilers are also really good. There's a bunch of different trade-offs between them, and a lot of it depends on what's there with your individual use case. So what we often find is that there's a really common workflow that you devs might go down. First, you want this high-level, sort of coarse-grained profiling information. We think OVR Metrics Tool is a really good example of this. There are other tools that can just tell you, at a high level, allow you to traverse your game, your app, just play it and see what's wrong. And then once you realize that it's getting into the red, frame time is spiking, then you actually want to dive deep into that fine-grained profiler, of which RenderDoc is a really good example. So over the next 10 minutes, and actually 20 minutes, we're going to go through 2 individual case studies, which are going to marry this concept of us showing you these really cool hero perf tool features. How to use RenderDoc, how to use a tool like Perfetto. But what we're also going to do is show you how we actually use the tool to optimize GPU and CPU perf in ways that previously weren't there. And the reason we're doing this is just really the principle of showing, not telling. Yes, we could tell you, oh, we made Unity, N% faster. Yes, we could tell you that RenderDoc has these 10 new features. But the best way for us to demonstrate that is just put them together and go one by one to see how that tool was the only reason we were able to make those optimizations. So it's really going to be a set of applied case studies the next 20 minutes. So starting off with Unity, the universal render pipeline. Who here uses the Unity URP right now? Really good, quite a lot of the audience, I'd say the majority. Who else is in Unity but uses a modified SRP? So not the built-in render pipeline, but really a custom scriptable render pipeline. Okay, not many, honestly, which is a great sign because we highly recommend it, we and Unity both. What we found in the past is that at times, the reason why a few devs have had to actually modify the SRP directly, it might be because of performance or customization reasons. And that's why we in Unity, we have a really close partnership with Unity. We really set out to see how much performance could we squeeze out of it from the ground up. And the best part about this is that these are wins that we were trying to make that would then scale to all of your apps. You truly would just need to adopt that next version of Unity, the next version of the URP, to get all of the wins that we're about to show you here. So there's that pretty exciting case study, how we landed just a series of wins that are going to go straight to your apps, and specifically how those Quest performance tools enabled it. So starting with the basics, which is surprisingly has a lot of steps. The devil is in the details here. You want to measure your frame time accurately. And it sounds pretty obvious, but the idea is that if you don't have a ultra low variance number, 12 millisecond GPU, 10 millisecond GPU, that you can trust to accurately represent how much your frame time costs at any given point in time, you're going to be seeing measurement variance. Sometimes it might be 12.5, sometimes it might be 11.5. You're not going to know whether that variability is due to any change that you made, which is what you really want to narrow down, versus due to just inherent variability in the first place. So the checklist you're seeing there is specifically how you reduce that variability. Very first thing is to lock CPU and GPU frequencies. We actually have a setting which we've documented online that locks a little bit more than just that, like memory frequencies. And this is really important because a lot of these frequencies they're implemented under the hood in the system via techniques known as a governor. The idea with the governor is that it's going to pick the right CPU, right GPU frequency based on a whole host of factors. Sometimes it's thermal conditions, maybe the device can thermally throttle, it's seen in many different platforms. You don't want any of that to distort your performance measurements. You want it to be fixed. So for the purposes of profiling, just choose a baseline value and keep it there for all of those measurements. Then you want to lock your head position, which seems obvious, but it can wildly distort your measurements if you don't do that. Because if it's not locked, let's say you turn 20 degrees to the left, now there might be 50 more draw calls. There might be way higher res textures. You very much don't want to measure a different number because like we said earlier, measuring that different number means that you want the tools to actually be telling you that something changed. And the next two are rather similar. You want to lock fixed foveated rendering, very similar idea. And you actually want to disable the compositor, which is our VR graphics compositor. Even though the compositor is a really important part of how VR works, it's where time warp is performed, really good for latency correction. So even though that's true, for the purposes of measuring the performance of your app, You just want that more stable measurement where there's like almost no preemption, no interference. So then as for which tool to use, there's a bunch of different possibilities. There's even more than what we outlined here, but two really good ones we like. As we said earlier, OVR Metrics Tool is really good for that coarse-grained, view while you're traversing your game. You can quickly see what's wrong, see what's in the red. But then this command line CLI tool, very easy to call, is OVR GPU Profiler. We also recommend that just to get that accurate frame timing, frame to frame. So once you've used what we just outlined in that previous slide, you're going to be in your workflow and you're going to realize that the frame is slow. Maybe you're seeing a bunch of red in OVR Metrics Tool. Maybe OVR GPU Profiler just told you that the frame is 14 milliseconds. So it's pretty obvious that the next step is to try and optimize it. And this is where we feel that tools like RenderDoc really help. Because if the previous tools tell you the what, RenderDoc starts to tell you the why, the how. And what is the series of operations that even adds up to that 14 millisecond frame time? So the very first thing that we find a lot of you devs will end up doing once you load up a tool like RenderDoc is ask what draw calls are even slow to begin with. Because your frame time is generally, other than a few things like pipeline overhead, your frame time is generally just the sum of the cost of your individual draws. So RenderDoc draw call timing is quite useful for this. We're not going to get into the nuances of exactly how this is calculated. You should definitely check the documentation online because there are a few different approaches. But the idea is that through the event browser or through also our real-time per draw call metrics, you can get a pretty good view of how long that individual draw calls are taking. So what you're probably going to want to do is follow a workflow where you get those per draw call timings, and then as you can see, the draw that's highlighted at the very bottom is the one that in that given render pass, the render loop.draw, that draw call is the most costly. It's 1 millisecond. It's even more than a millisecond out of about 1.5 total milliseconds for that render pass. So now it's time to actually dive a little bit deeper into that draw and see where things went wrong. And by the way, even though this particular screenshot is using OpenGLES, at this point we recommend every one of you devs to be using Vulkan. So the RenderDoc shader viewer is a really good next step because it's one of the most essential parts of understanding the why. There are many reasons why your draw call could be slow. Some obvious ones are that your textures are way too high res or that your meshes are too complex. But maybe the most common one is that your shaders are doing too much work. And the RenderDoc shader viewer is a great way to actually view that shader code. But we think the hero feature in RenderDoc there is not just the view ability, but the edit ability. Because I'll challenge everyone to try and find anywhere else on our platform where you can make shader changes that quickly and get the instant feedback that quickly. Because it doesn't just let you edit the shader and validate that it works. You can actually see the rendered output. You can see whether the shader did what you want, and you can remeasure the frame timings. So if your frame was 12 millisecond, you think you have a great optimization in your hands, just edit the shader code directly there, validate whether it went down to 11.5 or whatever you're trying to do. Whereas if you're not using an instant iteration time workflow like that, it might take minutes to rebuild that APK inside the game engine of choice. So that workflow alone enabled a bunch of key wins that we in Unity partnered together to land in the URP, and now we're going to go one by one through them. So the first one, for the next few minutes, we're going to go really deep on these shader nuances. Don't worry if you're not someone who looks at shaders that much. That's actually the very reason why we in Unity partnered to do this. You're going to get these wins for free, but a lot of you also like modifying shaders, so hopefully you'll find the next few minutes pretty interesting. So for this very first one, we found a way to optimize the output alpha calculation, which, as a quick primer, it's one of the last lines usually in every shader file. It's how you actually set the alpha channel. And of course, you're trying to set the RGB and alpha channel in most fragment shaders. So there's a rule that it's not a hard and fast rule, but it's way more true than not, that dynamic branching in these shaders is going to be bad for performance. One of the reasons is that it causes something known as warp divergence across these branches. We don't need to get into all the details, but it's quite useful in general to conclude that you don't want too many of these if statements if you can help them. And that's what a dynamic branch would be here. So if you look before in the pre-modification shader code, it was doing an if statement that really wasn't providing that much value. It was just checking if the surface type was transparent. And this is one of those things that you can actually know ahead of time. And if you know it ahead of time, you don't even need that if statement at all. You can solve that with shader keywords, which is exactly what we did on the right. Now that check on the right is something that evaluates really at compile time ahead of time so that you don't actually have to do work while executing the shader for it. So this one, as you can see there, it saved 0.14 milliseconds in the GPU in a pretty representative benchmark scene. Most of these measurements that we're going to share in the next few slides were in a benchmark scene that we think quite heavily mirrors the average VR app. Then we found a somewhat similar optimization, quite similarly sized win, but in a different part of the shader. We found that Unity's URP shaders by default had this check for whether or not you were using orthographic projection or perspective projection. And that would be good if, hypothetically, you had the need of always switching back and forth between them, and if there was really no way to know ahead of time which one you were. But what we found is that most Unity VR apps, and probably most Unity apps overall, are going to be using perspective projection most of the time, and it's going to be known ahead of time. So instead of actually having that costly check here, this is kind of like an if statement. It's actually comparing this W channel to 0. We can eliminate it and just know it ahead of time by checking for this meta quest ortho proj, which is that shader keyword that is very much known ahead of time for the shader. So in this case, we saved a total of 0.23 milliseconds, again, in a pretty representative benchmark app that we think is going to scale to hopefully pretty much all of your apps. And as you can see, the way we've written this, right now we're gating it by meta quest, and in that else block down below, that's going to be what the shader does without our optimization. The third one gets pretty interesting. These third and fourth are also, quite similar. The third one's about dynamic shadow rendering. So there's a lot of stuff that goes into to these algorithms for dynamic shadows. One of the main ideas is that you generally don't want pixels which are not going to be have shadows cast upon them. You generally don't want those pixels doing a lot of work during your fragment shader to calculate what the effects of those shadows might even be. Sounds kind of obvious, but we found an area where the URP shaders by default were doing a little bit more work than they needed to. So the idea here is that you can tell whether a given pixel, any given pixel when you're actually rendering it in the fragment shader, you can tell whether that pixel is back-facing to the shadow casting light. And if it's back-facing, by definition, it means it's not going to be affected. And if it's not affected, you then want to save all the computation. So the way to tell that is by taking the dot product of that main light's direction with the surface normal of the actual pixel itself. And if that dot product is negative, here we just set this shadow coordinate z value to -1. And the next slide, you're going to see that when it's -1, when it's negative, we are going to then skip a really expensive part of the normal dynamic shadows algorithm. And that expensive part often involves multiple texture sample operations. It depends on what you're doing in dynamic shadows. Sometimes if you're doing something like PCF 5x5 filtering or whatever other technique you're using, there's a lot of work that goes into it. So this is basically an early out. We're early outing of a bunch of texture samples. And there's something really ironic in what we're sharing in this slide, which is that we actually added a dynamic branch to make the code go way faster. And we just told you a few slides ago to not use the dynamic branching, and it's just an illustration that one size doesn't always fit all. Like, yes, dynamic branching generally does cause perf overhead, and it was very true in the first two examples, but in this case, the benefits you were getting by skipping the work that was gonna then be gated behind the dynamic branch, those benefits outweighed that slight cost in dynamic branching itself. So it was a really big win. We created a contrived sample scene. So very strong keyword. It was a contrived scene. It does not scale to the average workload of your apps. But in that contrived scene, we created a test project that had one large surface that was heavily back-facing to a given light. So in that scene, it was a perfect test bed. We wanted to verify that if we had made the shadow optimization properly, that scene would get way accelerated. And it did. In that scene, it went from 4.96 milliseconds to 3.35 milliseconds, which is obviously a huge win. Now, major disclaimer there that that type of win will not be seen in average content. However, we do think the real-world gains will likely be significant because the average app probably has a decent number of pixels that are going to be back-facing to that light in the first place. We then made a quite similar optimization, but that had nothing to do with dynamic shadows. And that's pretty important because not all of you are going to enable dynamic shadows. In fact, we might guess that most of you don't, because it's actually pretty expensive today. So if you're not enabling it, that's still a perfectly valid design choice, in your art style. And we decided to apply a quite similar optimization to the normal lighting calculations. So what you're going to see there is we're taking a pretty similar dot product, like second line in that, taking the dot product between that surface normal and the light direction. And if that dot product is negative, we can also skip a bunch of normal lighting calculation work. So not just shadow map samples, but general lighting work in the forward pass. And in this case, it was also a pretty substantial optimization, 200 milliseconds, or 200 microseconds, 0.2 milliseconds. So the thing we really want to highlight here, as we said earlier, RenderDoc enabled that immediate iteration. We were able to scan the shader. We had many more ideas than actually worked out. And the only way to actually reconcile that is to try all of them one by one and to get pretty much no cost during that iteration. We could try it out. Maybe it failed 10 minutes later, and then we moved on to the next idea, as opposed to being subjected to that 20-minute, 10-minute, 5-minute, whatever your APK build turnaround time is. We were able to skirt around that entirely. So something you might be seeing is, you might be wondering whether we always have to go line by line to find shader wins. That's always a good technique. If you really care about getting into the weeds, it's good to know what's going on in your shaders. But you don't always have to go to this level of complexity. And this is where a feature that we've introduced quite a while back, known as shader stats, might really come to the rescue. So the idea there with shader stats is that it really decomposes what's going on in your shader down to a few main ideas. Because yeah, your shader code might have a lot of lines, 500, 1,000 lines are roughly comparable depending on the complexity of what you're doing. But there are a few things that really matter above all else in that shader. How many texture samples is it making? How many registers is it using, which is going to really affect occupancy. So the nice thing about shader stats is that it gives you immediate feedback on all of those. You can see a number like, is my occupancy just terrible? Is it below 50%? And that's a warning sign to know that you should do something about it. We're happy to say that there's also an in-engine workflow, both in Unreal and our Unity SDK. And it's pictured like what we see there. That metric at the very bottom, the ALU fiber occupancy percentage, is going to be the metric of choice that we used to make this very final optimization. So that's a very important metric, just high level for people who have really spent a lot of time handcrafting shaders. You might be familiar with this concept of occupancy. But the idea is that GPUs have these techniques known as latency hiding. The idea is that if it's doing a lot of work waiting for a memory fetch to return, maybe it's made a texture sample that's so high res, the GPU would otherwise be stalled waiting for the data to return unless it can do other work in parallel. And one of the best ways it can do that other work in parallel is by ensuring that your ALU fiber occupancy percentage metric is very high. The lower it is, the more you're getting into the GPU's ability to schedule a lot of that parallel work. So that's why this metric is so important. And now we're going to find how we in Unity use that metric to make a pretty substantial one final win. So there's this Europe equality setting that allows the developer to only select one additional light per object. And we basically found that if that was set, we could prevent full loop unrolling and only essentially do partial loop unrolling. We don't need to get into all of the weeds in the shader code, but the idea is that if we did a full loop unroll, we were going to sort of snowball the shader register usage. But by limiting it to a partial unroll, the shader register usage was going to be capped, and by it being capped, it was going to actually help occupancy. So here's the really important part. Before and after, register usage went from 10 to 8, and occupancy, which is sort of almost the inverse of register usage, although there's a pretty complex formula for how one gets mapped to another, occupancy went up from 50 to 75%. So that meant that the GPU's ability to schedule that background work while waiting for those texture fetches to come back, that increased quite a bit. So the overall frame time in this very representative sample, we think, went from 4.63 milliseconds to 4.25 milliseconds. We hope it's going to cause pretty similar wins in your apps. So here's a recap of what you just saw last 10 minutes. We went through a pretty involved case study where we're not just pitching the tool to you, RenderDoc, we're pitching the whole workflow, because you all might need to make similar optimizations in your apps, But if you don't want to, great, just use the URP. There's a reason it's this nice base layer that you can all benefit from behind the scenes. These were made in very close partnership with Unity. We have a really close relationship with them. And they're going to be applied specifically to the URP shader library only when you're using the Quest build profile. And these are going to be there in Unity 6.5, which obviously hasn't released yet. Stay tuned for how you can grab these. So now, next 10 minutes, we're going to go through a somewhat parallel workflow, but actually in the CPU itself. So let's just take a shout out one or two answers. What are your favorite CPU optimization techniques or tools? So if you see something's wrong in your app, what's the first thing you turn to? OVR. Okay, so Akil stills, thanks. Who else? That's a great answer, yeah. In-engine profilers. So those answers are pretty much what we've seen most devs do. Either rely on in-engine profilers, which do provide a wide feature set. They're really good. The Unity profiler or Unreal Insights as well. Both are really good. And what we're going to spend the next 10 minutes doing is going through a case study of our system-wide profiler named Perfetto, which is Android's default system-wide profiler. And the idea here is that even though those in-engine profilers are really good and you should still continue to use them, Perfetto does have some unique features that might be able to turbocharge your dev experience, and we want to go through some of them. So it's a system-wide profiler, and that means that it really has these system events and application events in tandem on a shared timeline. It's a timeline view. As time goes on, you're going to see these events really fly by, and it allows you to trap application events like you can instrument code and function names, et cetera, via the track event API. So to really pitch it to you, we feel that there's this combination, this like quadruple grouping that you might not be able to get in really any other tool other than Perfetto. So first things first, it's an instant answer of where you're even bounded by, CPU or GPU. And yes, you may be able to get that in some other tools, but what's so nice in Perfetto is that you can really go frame by frame and see, show me why the GPU caused my frame drop. And you can see that, wow, the GPU work, you expected it to be 10 milliseconds, it was 13 milliseconds that frame. Perfetto is great for that kind of stuff. It's really good for giving you a full view of every thread running in the CPU system-wide. And yes, that can be daunting at times, but the other side of that coin is that information is sometimes unmatched if, for example, these system-wide threads are doing stuff that you don't want. It's also really good for this needle in a haystack workflow, where you can really zero in on one particular frame causing problems. I'll give an example. If your app is 70 out of 72 FPS, what do? You can't rely on a profiler that aggregates, that does things in the averages, because those two bad frames might get lost in the averages. You want to zero in on those two particular bad frames and see where things are going wrong, and that's exactly what Perfetto helps you do. And finally, it really allows you to combine CPU and GPU events in one shared timeline, which might be the best advantage, because often many other tools only really focus on one or the other. So here's that CPU scheduling view that we alluded to. Basically, the very top, it's a really nice grounding way of understanding where your app is even executing. The way that we assign thread affinities to your application is that we basically reserve the bottom half of these threads. A lot of it's of these cores. A lot of this is going to be dependent on which device you're running on. This came from the Quest 3, but overall, you can use a tool like Perfetto to see, oh yeah, I'm using cores 3, 4, and 5. You can see whether system work is interfering, stuff like that. Then there's this really cool per process breakdown. And the idea here is pretty simple. There's a lot of stuff going on in the system, but you probably want to narrow down specifically what your app is doing. Almost all of the CPU stuff that you care about would be directly what your Unity app, your Unreal app, or your native engine app might be doing. So select your app and then pretty much go to the next step. So now for the pretty exciting case study. We saw that in a particular perf bug that we were looking at, performance FPS had dropped from 72 to 67 on average, and enough to cause a pretty jarring experience. It was pretty hard to even understand what was causing the slowdown and how to fix it, and we truly believe that Perfetto was the only tool that could have diagnosed it end-to-end. Yes, other tools might have shown us what was going wrong, but to directly understand why it was going wrong and how to fix it, Perfetto is pretty unique here. So the first really nice workflow idea is just scan the timeline and find which frames are problematic. This is pretty underrated, but you can do this because you can zoom in and out really easily. So here we're actually zoomed out pretty heavily. You know, you're looking at every frame in sequence. And if you squint closely, and it's a lot easier when you're the one controlling it in the computer, but here if you squint closely, you might be able to see that the fifth frame from the left has a lot bigger of a gap compared to the other frames. Something's wrong. And that's where the early warning indicators come from. Something's probably going wrong there, so now it's time to zoom in and see what's going on in that frame. So once we zoom in, we can find that the main thread, which is really the most important thread on the CPU for all of your applications. You know, in Unity, it's called Unity main. In Unreal, it's the Unreal game thread. This is going to do so much computation, like, you know, game logic, C# scripts, all that kind of stuff. That is something you almost never want to be stalled. It is usually the thing that's going to bound your performance. But in this case, we saw that it was just sleeping for over 3 milliseconds on a given frame, which is, remember what David told you earlier, that you only have 13.8 milliseconds to hit frame rate at our lowest FPS, 72. At 90, you only have 11.1. So sleeping for 3.3 milliseconds it's a no-no. So Perfetto allowed us to see that something was horribly wrong. But more importantly, it allowed us to see why it was sleeping. And we don't need to get too much into, you know, how game engines and real-time systems are designed. But basically, these threads always have very tight dependencies. The main thread might often have a dependency with some job system thread, you know, some job worker thread that it's waiting on. And Perfetto allows you to visualize those dependencies extremely tightly. So we were able to go to the very end of the sleep. And the reason why we wanted to go to the end of the sleep is to see what actually caused the sleep to end, because that thing was probably what was responsible for the sleep in the first place, because it wasn't giving control to the main thread fast enough. So we wanted to go to the very end, see what woke the main thread up, and then see whether we could move that work a lot sooner so the main thread wouldn't even sleep to begin with. And then Perfetto allowed us to then go backwards. We found that a certain thread is what the main thread was sleeping by waiting on, and then we could trace that thread itself. And we really saw that thread was basically, it was a system thread running on these top 3 cores. Remember earlier I said that top 3 cores are often really, you know, earmarked for the system, bottom 3 for the app. In this case, that system thread was running for way too long, and it was blocking the main thread, the thread that's very much going to, you know, control your FPS. And the main thread wasn't able to proceed until that system work finished. So just to recap, in case that was a lot of words just flying by, the main thread, it basically did this anti-pattern in software design. It did a blocking call. It's fine to rely on other threads, but you probably don't want to be blocking. You probably want it to be asynchronous. In this case, it was something we wanted to fix in our own system through our OS, etc. It was doing a blocking call, waiting for the system thread to complete. The system thread was taking 3.3 milliseconds to even be scheduled before it could even run. And once it ran, then it could obviously do its work that could allow the main thread to continue on. So therefore, the main thread was really forced to sleep for that entire duration. And that was an instant frame drop. So what Perfetto really uniquely enabled in this workflow was that immediate diagnosis. We actually found that, you know, 67 out of 72 frames had nothing wrong. It was only those like 5 problematic frames where this work, that stall was really picking up. It allowed us to see the system threads, and if we hadn't seen this, we wouldn't have known why the main thread was sleeping. In in-engine profilers, you don't get that. In an in-engine profiler, we would have just seen that the main thread was stalled. We would have had no idea why. It allowed us to see the dependencies between threads. We didn't just see that the main thread was sleeping. We saw that it was directly waiting in one thread to signal it again. And finally, we were able to see the thread state that, hey, this thread is running at a given time. You know, that thread is sleeping. And obviously, when it's sleeping for too long, alarm bells would go off. So it's that type of performance investigation that we think it really might not get solved without a tool like Perfetto. So with that wraps up this case study part of our discussion. Now I'm going to hand it back to David to cover a lot of broad other tools.
Thanks, Neil. Yeah, these are some really powerful tools. And if you have the expertise, these may be second nature to you. How many people have honestly used RenderDoc before? Okay, a good amount of you, wow. And how many have used Perfetto to debug a performance issue on the CPU? Okay, yeah. So these are extremely powerful tools, as Neil just described. But they take a little bit of learning. And there's quite a bit of information to sort through in both cases. So you may have heard that Meta is kind of into AI, and we thought, what can we do for you on that front? Well, it turns out that AI does make quick work of a lot of these volumes of information. And it can kind of give you superpowers in terms of finding and root-causing issues. So we've given you a couple of tools recently that help in that way. So if you don't want to bother with learning, exactly what every color in Perfetto means, or how to manage the UI and do the zooming, frankly, it's non-trivial. Like playing a musical instrument. Once you master it, it's worth it. But these AI tools already know how to use it very well, and you can be very lazy, and you can just tell our runtime optimizer tool, find the bottleneck. And it'll just grab like if you have a Perfetto trace and you don't want to open it up in the editor, in the Perfetto UI, you can open it up in our new runtime optimizer tool. And that's a tool right inside of Unity, which can help you capture the trace as well. But that'll dive right into your app, look at all the different weights and utilization numbers across the period of your trace, like Neil was just describing, and come back to you with a definitive answer. So here in this case, we have an app that has actually pretty high load across a couple of resources. You might, at first glance, think that it's CPU bound, but it's actually GPU bound. The CPU utilization is high, but it's vertex buffer bound. So in this case, the AI assistant has actually parsed that Perfetto trace and done an analysis determining that the vertex utilization is too high, and made recommendations for mitigating that, one of which is to swap out your meshes. Another is reducing the cost of your vertex shaders, such as by using simpler movement on your tree leaves or whatever that vertex shader is doing. Then you can even do what-if experiments, sort of like what Neil described in RenderDoc. Here you can do modify and continue operations for more general and CPU-affecting parts of your project. So that's Runtime Optimizer. That's more of like a new assistant we've added inside of Unity, kind of a new UI flow. But what if you have your own flow? You have your own models. You're using GPT or you're using Claude Code. Well, yeah, we also have an MCP that will give you access to all of this same data. So this is where it gets really powerful. We'll kind of cross oceans of information to kind of just give you the answer you're looking for, and you can even tell it to watch for for example, main thread stalls. If you have an app and you're having a difficult time reproducing a performance issue, you can tell the AI, hey, sit here, I'm going to play this game for a few hours, and I'm going to try a few different things. I'm going to have a persistent session open. If you ever see main thread stalls, please let me know right away. Or if you didn't think to do that and you just had a bug and you want to quickly understand what happened, but you happen to have this thing open, you can say, and this is possible because we have a rolling buffer of kind of high-level Perfetto information, including all the different thread weights and dependencies in our system. You can retroactively pull the last 5 minutes of high-level Perfetto data and have the AI tell you what went wrong. So now, instead of having those hard-to-reproduce bugs or having to sift through oceans of information without really knowing what you're doing for a few days until you master Perfetto, you can have our MCP integrate with your known workflow that you're already using. By the way, how many of y'all are Claude users? Yeah, are you using Claude Code for daily? Okay, yeah, so this will slot right into that. Yeah, you can also cross-reference that with the logcat output. You can take a screenshot. So the MCP can actually enable your model to tell you, hey, you've got a sword that's clipping through the ground, and I see some physics gravity warnings in the logcat. That is why your CPU is getting bogged down right now. You should fix that, instead of having to spend 3 or 4 days or hiring an engineer to come bail you out. So this is super powerful. Yeah, so the MCP I mentioned, that is one of multiple MCPs. We have an MCP server that we've integrated that you may have just heard about in the recent talk. So MQDH, the MetaQuest Developer Hub, now has a view where you can get access to this and other MCPs. So the other MCPs, they give you access to things like our documentation, our samples, our developer website, and they can also contextualize things for you. Well, in this case, we have both a device debugging interface and a performance interface, and they can work together. Your model can put it all together and tell you exactly what you're looking for. So yeah, the new flow. I mean, this is changing a lot. Like, I don't even think how many of you were using AI aggressively a year ago in your development process? Yeah, I think this has kind of become the year of AI. I think we at Meta also have just been really leaning into this, and we would really encourage you to as well. It's a superpower. But yeah, you can now capture a trace. You feed it into your LLM. It'll tell you what's wrong. It may make some suggestions that you may or may not trust to fix it. But one way or the other, you get to a fix, and you can validate and continue, and hopefully save yourselves an order of magnitude or more of your time. But we also, I want to touch on some other, we get a lot of feedback from the developer community, and it's very important to keep you unblocked in all the friction that you're encountering. So we heard you, the resources on our website, on our developer center, some of our tools have high learning curves, and sometimes it's hard to find the information you're looking for. So if you're one of the people that's been struggling with that, I would encourage you to try again. There are now a new information architecture in place. We've migrated to the UI framework, and we've really streamlined a lot of the SEO and other aspects of that so that you can find what you're looking for more quickly and get answers to your questions more seamlessly. I really do want to plug that Unity, the MetaQuest build target that Neil just mentioned. That also pulls everything in kind of one place, so you kind of get all the wins that we've been enabling, and Unity's been a great partner on this. We, now right in the editor, as if you're, switching between iOS and MacBook, or if you're, switching between Android and PC, you can just have MetaQuest as your build profile, and that'll enable a lot of things that you might not have wanted to enable on another platform. This is in no way a lock-in strategy. I just want to be really clear that this is to reduce friction, and the reason that these are gated behind this is simply because they would cause trouble on other platforms. But anytime there's a win that benefits all the platforms, of course, we ship it there. So, a lot of you come up to me after these talks and ask, like, is something available cross-platform? The answer is yes. Anytime we can, we do that. I think that a lot of the wins we've described here, and even the Perfetto workflow and a lot of other things, will apply to other Android-based headsets. Right, so another thing that a lot of you use, and I don't even need a show of hands, I'm pretty sure basically all of you use Link constantly, right? So Link is our #1 developer tool. It's used by almost all of our developers because you get a relatively representative user experience in your app, and VR is a very novel user experience. You need to test all the designs you're doing in there without waiting for an APK to build and push. Just a reminder that all of the OpenXR extensions are generally available on Link for development. That doesn't mean that consumers can use it in shipped apps, and that's mainly because our consumer level support for Link is kind of descended from the Rift ecosystem that came up years ago. But for development for a standalone VR headset, we have essentially the whole OpenXR ecosystem available there. And you can meaningfully test your app's behavior just by switching. On Unity by default, it's in the Windows build target, and you can just hit play and see it instantly. We've been having a lot of feedback that the reliability wasn't too great there, that you could hit play, pause, play again, and it's not going to work. Actually, how many of you have experienced instability on Link in the last year? Yeah, it's been pretty bad, I got to be honest. We've been investing a lot in that. So I would ask you also to try again, because we've shipped a number of updates, even in just the last couple of months here, that should really, really increase your connection reliability and allow you to do more of those play cycles without that kind of debugging and disruption. I know that folks have had to jump through hoops. But yeah, if you're still having any trouble with it, the end of this talk will be all about how you can get in touch with us, because we have many support channels we want to hear from you, and Link is really a very important thing to us. Okay, we've also shipped a couple of tools recently that can help you track your app's performance after it's shipped. So one thing you can do is kind of collect aggregated, anonymized, privatized, performance data from the field. Not only how your app is doing individually, but you can kind of see how you're doing relative to other apps. But the important thing here is if something went out, you shipped an update, and there's a configuration you didn't test, and suddenly everybody's having stale frames and churning because it's a slideshow. That may be something that you don't get in your QA. You'll see it in your telemetry now. So these kinds of statistics are available for all the major resources we just talked about. So you have CPU, GPU, and memory utilization, as well as different types of stalls, and we can do percentiles and moving averages. So the time period, I don't know if you have used our analytics before, but at times people were frustrated with the short duration. These are longer now. You can view it over many weeks. So this should be a superpower for you detecting issues in the field. And again, you don't have to just wonder how you're doing relative to the ecosystem. This is, aggregate information like you might expect from other platforms, comparing, your app's performance to those in your category, those across the ecosystem. Unfortunately, you can't pick one other app because that wouldn't be cool if you want them to do that to you. But you can see how you're trending relative to the ecosystem. Okay, and one last tool, phased releases. You can do what we call A/B testing. So if you have a new change you want to roll out, you don't want to inflict it on your whole ecosystem right away, you can do a 1% rollout, and if it blows up, you just roll it back. So this is something we at Meta do quite a bit with our products, and it also gives us a lot of insight on the exact impact of a change we made. So if your engineer is saying, hey, I upped the graphics on level 5, and you want to say like, oh, how many millions of dollars is that going to make me? You can now find out. And once again, yeah, please check out our dev site again. As I mentioned, we've made a lot of improvements based on your feedback. In general, we are very interested in the experience you're having. We want to make sure that it's as smooth as possible. We want to help you make money and help you grow your success. And this is absolutely the early days of VR. So I think this is a partnership. And so we want to hear from you. And please let us know. We have forums. We have user voice. Our PMs and everybody in the company look directly at that. We talk a lot about the major pain points that come up. We have internal publications that try to aggregate that and understand the trends in what you're experiencing. So please do not suffer in silence. We really care. And yeah, you have a couple of channels you can go through if you're having trouble. So the first and easiest might be, just to use Google, use your AI agents. I use Gemini a lot personally. I find it to be like Google++, but Claude Code is really aware of a lot of these things too, and GPT. But you can self-host with a lot of the information we're putting out there with our MCPs and with our website. You can also engage with our community. So our forums are supported directly by moderators, and we also have fast paths to get to the engineering teams if there's a systemic problem. But yeah, just want to let you know, like we're very much listening, and please get in touch. So just to recap, a couple of best practices. I think that the dynamic resolution often doesn't get used as much as it should. That's a powerful feature because you can set a fidelity baseline and then opportunistically kind of make the app look better whenever it's possible. That does show to correlate with user engagement. We've also got dynamic CPU and GPU level management that you should enable. That's enabled by default, so don't worry. There are also a lot of workflows in Unity that you should be using. They're really good about teaching you how to do that. But I really encourage batching and minimizing CPU, GPU round trips whenever possible, consolidating your meshes and materials where it makes sense. Of course, there's a fine line. If you have too complex of an Uber shader, then you get other issues like state buckets and stuff like that. But yeah, ASTC compression, that's still a recommended technique since 10 years ago. And yeah, one other thing a lot of people run afoul of, I did see a few hands for that deferred rendering. Well, just be careful which post-processing effects you're using, because if you're sampling from across the frame buffer, that's still something we're not great at. Being a tiled renderer for cache efficiency, we tend to perform better for shaders that kind of look up and write in the same neighborhood. So that unfortunately means that Bloom shaders, SSAO, and some other things like that are not always feasible yet. But I do want to recommend everyone, how many of you need a Bloom effect and aren't able to do it right now on Quest? Okay, I highly recommend Doom 3 Bloom. That's like a stencil-based volume approach. There's some good implementations of it on the Unity Asset Store and Epic Marketplace. So anyway, we can talk offline about that. Yeah, so we had some, we had a lot of different topics here. And I just want to recap briefly that perf is vitally important. If you're not hitting frame rate, we have seen spikes in user churn. Your users aren't going to want to engage with an app that makes them nauseous, unless they do, but most don't. And then we have a lot of tools that you can kind of progressively refine issues. OVR Metrics Tool, I heard a lot of people calling that one out. Yeah, that's the greatest hit, I think. But the tools like RenderDoc and Perfetto are where you can really get a deep understanding of what the system's doing. And so, my personal workflow, I often start in those high-level tools, kind of triage, and then use the appropriate tool for the job. So part of it is knowing what's available. or just using AI, and it'll figure it out for you. And once again, we have a lot of infrastructure tools available for rolling out your app. Please do get in touch with listening. Okay, thank you.
And we'll direct everyone to scan that QR code, please. And by the way, we have 5 minutes for Q&A, so please queue up. After those 5 minutes, we'll be right outside. We'll be here as long as you need to answer questions. Thank you.
Okay. Okay, so thank you for the talk. Right before GTC, I noticed that you have introduced the new frame sync, replacing the phase sync. Can you just talk a little bit about that? Because, for example, it seems like it was going to deprecate the application SpaceWarp, and I'm not sure if that's true or not, if I'm misleading the blog. So if you can do some talk about it.
Yeah, hey, that's a really good question. So frame sync is a technique that we use to balance like the latency of the rendering with the amount of GPU that you have to do the rendering. So the idea is, we want to kick off the frame so that it finishes right before you see it to minimize latency. But if we screw that up, then you don't get enough GPU time to do the work. And so it's really related to like adaptive frame rate like you would see on desktop. But it's also a latency mitigation technique. ASW, on the other hand, allows you to completely skip every other frame. So the idea of that is just to free up more GPU headroom and CPU headroom. So yeah, you would use them together.
And I think the concern is whether you were concerned that we were going to deprecate application SpaceWarp, but we absolutely are not. The two features can work in tandem. Yeah. Thank you.
First, I want to say thank you, Neil. You're one of the unsung heroes that make the behind-the-scenes like shaders run efficiently, so that we don't have to do all that work ourselves. And glow effects. What is the best way to do them? Like, is it still like fake it with a plane, or could you use post-processing? Like, I know you. That's like a big.
Yeah, so there's a couple of techniques for glow. On a tiled architecture, you're really going to want to, so it depends on how much glow you want. If you just, like we see some lights up here that have quite a bit of glow around them, I would just use extruded geometry and then, stick that on top of those. But if you have like HDR bloom, where like most of the scene should be blooming around everything else, you're probably going to want to use a reduced resolution render target, and then do it there and try to do a nicely filtered composite back.
Okay, cool. And will I be able to ask AI to do that for me soon?
I'm sure it can right now. Yeah, you should try it. Actually, yeah, AI should be able to tell you all about both of those techniques.
Okay, sweet. Thanks.
Cool. 2 more minutes, and hopefully we can get through all 4 of these questions, and we'll answer everyone else outside. Thank you.
Hey, so I never had an interest in game development until I put on a Quest headset, and that alone made me want to build something. But when I go into the meta doc sometimes, I feel like, I guess I'm just like, who is the developer that you're writing this documentation for and building these tools for? Because sometimes I read it and I'm like, oh, this is written for a game expert who's converting to VR. And I just like, you're in such a unique position where you like own the hardware stack, like the software. And so I just wondering, have you ever thought about like making some sort of academy for people who are new to game development or something like that? And like who's like the person that you're developing for right now?
I think what we'd say overall is that we care deeply about all different skill levels of developers. Me and David are right now more in the performance, Unity, graphics, et cetera side of things, but there are a few people in the audience, like Joe back there. He's done a lot of work with the Developer Center in the past, and there are some others I think you could get in touch with. So
who's Joe?
Joe's the one sitting back there. Putting Joe on the spot here. But what I'd say overall is we care deeply about that indie developer, that solo developer who might not be an expert in a lot of different topics. The documentation needs to cater to everyone. So yeah, thanks.
I should add, I think all developers really go through a journey, right? They start out just having an interest, it's a sparkle in their eye, and then they learn more about it, become an expert, and hopefully make a lot of money and find their voice and achieve a lot. And we're here to partner with you and guide you through that journey. So some of our resources are for people at different stages in that pipeline. We have a lot of videos and we have a lot of onboarding materials that would be for someone who's newer. And part of it is we want to help you get excited about it and then figure out what you want to make. And
Maybe add a skill level tag. Thank you so much for all your work. I appreciate
Thank
it.
you. And last question right here, but the other two, really sorry about it. We would love to take the questions offline. Thank you.
The MCP tools and the AI tools that you have mentioned, is it possible to use that on, say, a typical Android device?
Is it possible to use it on Android?
Yes, because essentially it is Android, right? Like.
Well, so you can run the Godot editor on Android, and there are some models that will run at performance on Android. But the ones we just presented are kind of coupled with MetaQuest Developer Hub, which does not, as well as the runtime optimizer that runs in the Unity editor. You could do crazy things and like run Wine and try to run that, but it's going to be pretty slow. But that's a good idea. Thank you.
Thanks everyone for your time. Reminder, please scan that QR code to give feedback. And we're going to be huddled up here for the next hour. So please ask us whatever you'd like there. Thank you.